The penultimate algorithm for this chapter is what we refer to as Fleury's algorithm, which is basically a step-by-step procedure for finding an Euler circuit and Euler path. Now, I personally don't want you to necessarily focus on this algorithm because I think it's intuitive enough without really needing it. But let's just walk through it, and then again, as an example, we want to actually find an Euler path or Euler circuit in a graph should it exist. So what Fleury's algorithm says to do first is to count the number of odd vertices in the graph. And as we practiced, right, we see the relevance of that because the number of even and odd vertices will help us know whether it's possible or not. So in the case 1, when you have no odd vertices, an Euler circuit exists by Euler's circuit theorem. In the case 2, when 2 odd vertices exist, an Euler path exists by Euler path theorem. And in case 3, if there's more, neither exists due to both theorems combined. And again, 1 and 3, those are not possible cases. So this is the only thing, there's only 3 things that could happen. And we're either going to have an Euler circuit or a path or neither. Then once we've determined whether or not it has them, then we can actually find it. That's kind of the point of this algorithm, is to actually determine the path and theorem. And so basically, where am I starting is the first question, where in the case 1, if it has an Euler circuit, you could start anywhere in the graph. But in case 2, if it's an Euler path, it has to start at an odd vertex, which is something that's important to remember. It will not work if it does not. Then what Fleury's algorithm says to do, and this is why I think it's not particularly helpful, it says to travel along the edges of your choosing without deadheading. So of course we're not going to deadhead because that's going to defeat the whole point, right? The whole point is to find an answer that does not deadhead it. And basically, it just says do what you want, travel the edges on your choosing. It says don't cross a bridge unless you must. And that's because a bridge, technically you can't have an Euler circuit if there's a bridge, but you could have an Euler path with a bridge. A bridge is like it's the only edge that connects the two. Once you cross it, you can't go back. And basically, it tells us to avoid a bridge. But um, there's other tips which I think are important, which are not described by Fleury's algorithm, which I wanted to show you. And I want to actually do a few examples here as well. And that's what it says to do as the next example is use Fleury's algorithm to find Euler paths and Euler circuits in the prior examples. So let's move back to the packet and do so. Okay, and so in these graphs, we've already determined whether they have Euler paths or circuits. So that's step 1. We've already done that. So in this first graph, we know that this had 2 odd, therefore it had an Euler path. And in that case, we must start at one of the odd vertices for our starting point. So if we remember, those were G and F were the 2 odd vertices in that graph, we got to start at one of those. So let's just say we're going to start at G because we don't have any other information, but usually you would know where am I starting if this was a real problem. And basically it says to travel along the edges of your choosing. So let's just say we go left first, and basically our goal is to just formulate a Euler path. Basically I want to start at G and I want to end at F because I have to. And it will not work otherwise. And like a lot of the time we don't really have a choice of where we're going. Like if I'm going to go to H first, I kind of have to just travel along because I have to use adjacent edges. There's not really much choice. There's no options for where to go. But in a case where I have some choice, you typically can go whichever direction you want. It is possible to box yourself into a corner though, if you're not careful. So my recommendation is to try to completely cover every edge that you see before you move on. But usually it's not that big of a deal. But anyways, if you're wondering where do I go next, well, technically you can just go wherever you want. So let's just say I'm going to move this way and this way next. Also, usually what I recommend doing is labeling your steps. That way, if someone was to try to follow along with your work, they can kind of tell exactly what you're doing by following along with the numbers. So basically, I'm going to number each edge that I'm using and use an arrow to follow the direction that I'm traveling in this Euler path. And basically, I would just keep going. I would be step 6, F would be step 7. Again, here, notice that I'm actually at F, which was the end goal, but I'm not done because, again, I have to hit every edge. That's what an Euler path is, right? The definition is a path that hits every edge exactly once, starting and ending at a different point. But again, where should I go? What I would recommend is trying to be thorough. So maybe I'll go this way next, and then I could go up to back to B on step 9, step 10, and then I'll kind of keep moving. 11, 12, 13. And really, assuming that you check to see whether it had an Euler path or circuit, it should just work. And notice that I'm not done until I hit every edge. So while again, I'm back to F, once again, I'm not going to be finished until I hit every edge. So I need to go up to C and back to F for the final step. And that would thus finish my Euler path. And again, assuming that you check for how many odds it has first, it should be pretty easy to determine an actual Euler path or circuit, whereas it just sort of works, it just sort of flows. And that's the beauty of evenness. If it's even, it flows, you don't get stuck. And when we have two odds, we can start and end at different points because we're starting one and ending at the other. For starting and ending, odd is good if we don't want to come back. And that's why two odds are necessary in an Euler path. But anyways, we can see that it worked because everything has been used and it makes sense. And this would also be exactly the right way to show your work on an exam, because I could go and follow along your steps 1, 2, 3, 4, 5, 6, 7 and see, does this circuit actually make sense, or in this case, path. So looking at another example, in this graph, it had 0 odds, which we concluded would have an Euler circuit instead. Sorry, I wrote that really poorly. 0 odds. And by Fleury's algorithm, in that case, when I have no odds, there's going to be an Euler circuit, and I can start at any vertex. So I could start wherever. Let's just say down here. I did not label them, which also, just before I move on, notice that I could have described this circuit, or this path, sorry, separately by just listing the vertices. So another way, graphically I can see it, I think this is the easiest way to do it. You can also describe a path by listing, well, G, H, A, B, G, I, J, F, G, B, C, D, E, F, C, F. And that's another way of writing it. But, it gets really long and horribly messy. And to me, that's a lot harder to follow than doing it this way. So this is kind of my preferred way of writing out a circuit. But sometimes if you're thinking about your online homework, it's going to be hard to do this sort of thing on a homework, and they could ask you to represent it like A, B, C, D, E, F, G, or whatever instead. But it's really the same idea as a path or a circuit that I described in the earlier videos. Anyways, in this case, they're not labeled, which, as I said, this is bad. So if we're trying to write it that way, we can't because we have not labeled the vertices, which is why you want to label the vertices using letters, but do as I say, not as I do, right? Anyways, you could see that an Euler circuit will work just naturally here because, again, they're all even. Notice that technically there is a way to do it wrong, and that's what I wanted to mention, is when you're moving along randomly, as Fleury's algorithm says, notice that I could go back to the start here, but this would be a problem because in this case, I'm returning to the start without really finishing the Euler circuit. I have left some of it off. So this is what I recommend, is to try to be complete, and usually you want to avoid going back to the start until the end. Because once you head back to the start, there is you could possibly box yourself in. And that's another general principle that you'll see I use when I'm solving harder problems in later guides. But this would be our example of an Euler circuit. And again, you can label that as 1, 2, 3, 4, 5, 6, 7 in this case. And I'll leave this one as an exercise for you to practice yourself. But that one has an Euler path, and it should have started and ended at the 2 odds.